Here we go. We're diving into the end of chapter 15. I wanted to highlight something really quickly. We ended yesterday on the enteric nervous system, which is this set of nerves that will deal with digestion. Like the intestines and the stomach and the liver and all these places have their own digestive system. Well, what if that's not functioning? Well, your textbook gives you this whole little clinical connection or application talking about that. It's called Hirschsprung disease, which is a hereditary defect, meaning you don't have this enteric nervous system. And what happens? Well, then the colon, the large intestine, and the small intestine can't move the food through it. Right? Because that's one of the big things this does, is it helps move the food through, as well as secrete the right things to break down the foods and get the nutrients, right? So the ultimate piece is that the feces becomes compacted, and you get constipation, right? That you cannot have a bowel movement. Which you say, okay, that may be uncomfortable, but what's the really big deal about that? No, you can actually have people die from constipation. Sounds crazy. But it can, because that just continues to build up. You can't get it out, right? And that can actually cause gangrene of the colon, like the actual tissue around it dies. If that were to perforate or to open up, then all of that feces gets into the stomach cavity. These are bad, bad, bad things. Okay? So you say, oh, a little constipation, no big deal. No, it can be a huge deal. Okay? And usually, this is you're noticing in newborns that they're not producing bowel movements. Like they're just not having it. And this is supposed to happen. It can be a couple of days worth of time, and then slowly they have a huge blowout, and oh, okay, everything's okay. But if it's gone on for more than 3, 4, 5, 6 days, okay. It's time to see what's going on, because it might be something more impressive happening there. It is impressive, let me tell you. Yes, I'm going to stop there before I embarrass my children. All right, moving on quickly. Talking about neurotransmitters into section 15.3. This is what we talked about yesterday, right? In the plays or the little skits you all did, which again were very well done. I have to admit, I really enjoyed seeing your creativity about how you brought these things to life. Just fantastic. No, I salute you, definitely. It's well done. It's well done. So two contrasting effects, right? Sympathetic and parasympathetic, right? And for the most part, they're doing opposite stuff, right? And there's a reason why, is because usually they're submitting different neurotransmitters. And so one has one type of effect on the organ, one has another type of effect on the organ. And those two effects tend to be opposites of each other, right? So the different neurotransmitters is one way, but then we also learned yesterday that the same nervous system can have opposite effects on the same organ. Well, how does that work? Because there are different receptors on that organ. Based upon the different types of receptors will then form a different type of reaction. Does that make sense? So let's talk about those two main ones. The first one is acetylcholine. We've talked about this before. ACH is the abbreviation for it. And that's secreted by all of the preganglionics. So sympathetic and parasympathetic. The preganglion, remember those are the fibers that come from the spinal cord to the synapse, the ganglion. All of those preganglionic fibers and the postganglionic parasympathetic fibers, they secrete acetylcholine. And remember all the nerves that we studied about before, the somatic nerves, so acetylcholine is the main piece that they use as well. And they give you these names here. You'll hear these in the future, but just so you see them, I didn't put them on your study guide, but they are there. That axons that secrete acetylcholine are called cholinergic fibers. And the receptors that take on acetylcholine are called cholinergic receptors. Again, acetylcholine, it's playing off that choline piece. Yes? Sorry? Secrete means to give off. Yeah. So, two types of receptors that are these cholinergic receptors. Keenan, did you want lunch today? Okay, it is Haystacks. Good. Okay, sorry about that. Two types of these cholinergic receptors, and that is the I practiced these names earlier today, honestly, and I can't quite get them right here. Muscarinic receptors. These are from cardiac muscles, smooth muscles, and gland cells. They have these kind of acetylcholine receptors. And then the next one is called nicotinic, like nicotine. Right? That's where it comes from. That's where how we studied it, is from that piece. And that is on the postganglionic neurons in the adrenal medulla and the neuromuscular junctions of the skeletal muscles. We're dealing with those kind of acetylcholine receptors. And those are usually exhibitory and, not exhibitory, excitatory. And the muscarinic are both exciting and inhibiting. Can be either of those pieces. So that's acetylcholine. That's our first neurotransmitter. The second is norepinephrine, or NE. And by the way, these hormonal people, they love to use abbreviations because they have these huge long names and they just make them letters or numbers. So norepinephrine is secreted by nearly all the sympathetic postganglionic. So remember, the parasympathetic postganglionic, it secretes acetylcholine. All of the preganglionic, they do acetylcholine. Norepinephrine is just being released by those sympathetic postganglionic fibers. And they're also called adrenergic, another word I had to practice this morning, adrenergic fibers, meaning adrenal gland, right? The same word as adrenal, adrenergic fibers. Two different types of receptors, the alpha and the beta. That's how I wrote them on your study guide. The alpha adrenergic receptors and the beta adrenergic receptors. Alphas are usually excitatory, betas are usually inhibitory. There are tons of other neurotransmitters that are released other than acetylcholine and norepinephrine. Your textbook hits a couple of pieces of those to tell you a little bit about them. I didn't feel as if we had to spend a bunch of time memorizing a list of these different pieces. But I'm just telling you, these aren't the only neurotransmitters. These are just two of the big ones. And so that's why we're spending our time there. Any questions there? I would be remiss if I don't at least point you back at table 15.5 on page 567. Again, not asking you to memorize this whole list, but I would spend a little bit of time. Yesterday, we went through this, went through the whole table in our little skits we did together, but at least make sure you spend a couple of moments just taking a peek at that. So again, you see this. When one is exciting, one is inhibiting. That's usually how this parasympathetic and sympathetic are working.
Does epinephrine have to do with the heart?
There is, yes. Mm-hmm. Yep.
Can you give epinephrine?
It can.
Okay.
Mm-hmm. Yep. Yeah, as a way to get the heart muscle going.
Okay.
Absolutely. We good? Okay. We're really into almost the last bit here. Dual innervation. So most organs get both sympathetic and parasympathetic fibers coming to it. And usually those fibers have an antagonistic effect. Go back to our conversation about muscles way back in the day. An antagonist. What does that mean? Opposite direction, right? So if my biceps is doing elbow flexion, what's my antagonist? My triceps doing elbow extension, right? So this is the same thing. An antagonistic effect means if one's increasing something, the other is decreasing it. If one is exciting, the other is depressing. Does that make sense? And so for the most part, that's what they do. But they can also have what we call cooperative effects. And if you're talking about cooperation, you mean you're doing the same thing, right? I'm helping you, right? If I'm cooperating with you. So that's simply what it means. These two divisions are both causing different, act on different effectors to produce the same result. Does that make sense? And both divisions don't normally innervate an organ equally. Usually you've got a little bit more of one than the other, depending on what this organ is really for. They give the example of parasympathetic has more influence on digestive. Well, that makes sense, because remember the parasympathetic is the resting and digesting system, right? Versus the sympathetic has greater effects on the ventricular part of the heart, the lower part of the heart. Well, that makes sense too, because that's the part that pushes blood to your whole body. And if you want to run or fight, you need lots of blood. Make sense? I talked briefly more about this antagonistic and cooperative piece. Again, I'm not looking for you to know these. I just give you some examples of the heart rate and the pupils dilating. We talked about that yesterday. I think that was Autumn's group that did that piece with the pupils. Cooperative, again, two divisions act on different effectors to produce a unified effect. So here you've got the parasympathetic working on some of the salivary serous cells, and the sympathetic working on the salivary mucus cells, both of them causing you to have increase in saliva. Again, they give you an example of the pupils. This is in your textbook there on page 568. So you see it. You can have some pieces that do not have dual innervation. Okay? Some effectors only get fibers from one or the other, and you can still get this two different kind of reactions based upon how these fibers innervate, based on the receptors that are flowing. They give you some details there. Again, I just want to make sure you're aware that you can still get this opposite effect, right? Part increasing or part decreasing. Again, based upon how the fibers are running or what receptors are being used is basically what it boils down to. Any questions there on the target organ effects? Again, acetylcholine, norepinephrine, dual innervation. That's kind of the three big pieces from that section. I've just stunned you into silence. Wow, impressive. Must have been all that conversation about constipation earlier. Just stopped you all up. Huh. Good. Moving on quickly. Moving on quickly. Last but not least, we have the central control. Can you tell I've been awake since 5:30 this morning? Yeah, absolutely. Central control. No, that was by choice, actually. I went to work out. It's crazy. I'm the heaviest I've ever been in my life. I am not happy. So we're trying. We'll see. We'll see. And the only time it works is do it in the morning, which is terrible. But it's life. Because I get home from school, I don't want to go work out. Right? I want to sit on the couch. But I got to do work, right? But that's okay. But after I do that work, I don't want to go work. Anyway. So there you go. Recorded for posterity. Yes, so pray for me. Pray for me. One day down. I'm sore, but it's good. I'm awake. We'll see what I'm like by 7th period. That's the question. That's the question. Okay, central control of autonomic functions. This is it. This is like a little 5 or 6 paragraph piece on the very end of page 570 that we're dealing with here. So autonomic nervous system, you may think because the name of it is autonomic, in other words, I am under control of myself, that's what autonomic means, that it has no other effects, like nothing else inputs it. It's like just this system in a little capsule that nothing else can touch, and that's not true at all. It is affected by the brain and the spinal cord. So in some detail, which I laid out for you again on your study guide, the cerebral cortex can influence this autonomic nervous system. And in particular, it does that through the limbic system, right? The limbic system is big on emotions, right? Anger, fear, anxiety. those pieces can cause you to do other things, right? If I am super scared, we start to get autonomic pieces that work, right? Hair stand up on the end, right? Our goosebumps, right? We may start sweating, we may get paler, okay? All simply brought on by an emotion. So this connection between, again, the cerebral cortex and the autonomic nervous system. Hypothalamus is a major visceral motor control center. Okay, all the nuclei for some of these big things like hunger and thirst and sexual stimulation, this comes from this part of the brain, right, this hypothalamus, but then that leads to these autonomic effects. Again, things like erection, things like movement of the stomach and increasing of the salivary glands when you're hungry. Does this make sense? The ANS also is regulated by the pons and the medulla in the midbrain. And because those guys have those nuclei for things like the cardiac reflexes and the vasomotor control, salivation, swallowing, sweating, bladder control, all the things we talked about in the brainstem, right? That those are very much autonomic pieces. So there can be some back and forth control. And last but not least, the spinal cord reflexes. Things like having a bowel movement or urination. That's what these words mean, by the way. Defecation. To defecate means to have a bowel movement. Micturition. Has anybody ever heard of that before? To micturate, that means you're going to the bathroom. That's what you all insist on doing with this little water bottle whenever we do these skits. It makes me chuckle. It's good. It's very real life. It's good. I like it. I like it. Okay, so those are reflexes that are integrated into your spinal cord. I want to make sure you understand this. You cannot stop yourself from having a bowel movement. You cannot stop yourself from emptying your bladder. I'm saying permanently. Like if I was holding a gun to your head and I said, if you go to the bathroom, I'm going to shoot you. You may last a couple of days. Bowel movements, you might even go a week. But eventually you have to go. Right? There's no way you can avoid it. Now, we have trained you to overcome that reflex, right? That's what potty training is. We don't want you just to go whenever you have to go, right? We want you to be able to hold it between blasted 40-minute class periods and do it in the 5 minutes between, right? Makes sense, right? Though I know that's still difficult. Just joking. You guys are good. Does that make sense? But if this was cut, and I see your question, if we lost this component of the autonomic nervous system control, again, somebody who's been paralyzed, when that bladder reaches a certain full point, it releases. When the bowels reach a certain full point, they release. There's no control that they can have over that reflex. Does that make sense? Question? Sure. It depends. It all depends on how much you're drinking. I guess I should say that. Okay? I always think about, I tell you where my mind always goes when I think about this thought of like you cannot hold this. I think about these folks that were in the concentration camps. Specifically, when they were taking these people to those camps. Are you comfortable that what the Germans did for the most part was they crammed them in these cattle cars on trains that you would put cattle in, right? And so they would literally put people in, so you could not hardly move. Like, it wasn't like you had all this space to sit and move around. You were literally crammed in for days as they traveled you from wherever you were going to the concentration camp. Now, obviously, you don't really want to have a bowel movement in front of everybody like standing like this, right? So you're going to hold it as long as you can, right? But eventually, you're going to have to go. There's just no way you can't. So that's where my mind always goes whenever I think about this piece. So urinary tract infection comes from the fact that there is some sort of bacteria that has gotten up through the urethra. Holding it is really not going to cause that. Urine is sterile. There is no bacteria in urine normally. Does that make sense? So I always chuckle a little bit when folks like, I know some germaphobe people who totally freak out about urine on the seat, like in the bathroom, right? So I don't prefer that, obviously, right? Okay, I clean it up, sure, but it's not like you're going to die from it, Okay? Because unless there's some sort of problem with that person, the urine is sterile. There's no bacteria in it. Does that make sense? Sorry? I don't know what, there's some sort of, maybe it's the uric acid that affects the jellyfish sting that kind of counteracts that. I don't really know the mechanism behind that. I think that's what it is, though. Okay. Sure, you can. You can. I have to admit, so I wanted to be an astronaut when I was a kid, and I watched this program about these astronauts going through this desert survival pieces, and you know they would drink their urine, because urine has an awful lot of water still in it. Okay, your body does a great job of trying to keep the water in. Okay, because water is super important for our bodies. We'll learn all about the system that does that. But you can. So when I was, I'm being honest here, when I was about 8 or 9, I drank a little bit of my pee. It was nasty. Ugh, it was terrible. Because I wanted to be an astronaut. And to be an astronaut, you have to drink your pee, right? So I didn't become an astronaut, obviously. Well, so ideally, sure, because that means there's very little other stuff but water, if it's clear. Does that make sense? But if you're talking about a survival type situation, and Bear Grylls does it just to get the attention. There's no need for him to drink the urine, but he does. Because it's so disgusting. We got to watch, right? But no, you can. Again, it's a diminishing returns, right? Because if the longer I'm without water, the more my body holds in that water, and any urine that comes out is super concentrated, right? So to drink that back again doesn't really give me a whole lot of water anyway. Does that make sense? So there's a point of diminishing returns. And if you get too dehydrated, your body just stops producing urine. Like it won't even give you anything. It's saying, no, it's too precious. I got to keep this stuff in. Almost like that. Could be. I don't know anything about that one, but I wouldn't be surprised. The Romans did some interesting things. Yeah, and I mean, for you and me, things like urine and feces, oh, this is so disgusting. We have this little place we go to deal with that, and we never talk about it again. I mean, back in the olden days, this was just part of everyday life. There wasn't a certain place you went to go use the bathroom, and you had to deal with it. Does that make sense? So I wouldn't be surprised if they used it. Yeah. Yeah. Question? No. Good. That's where I want to stop for today as far as lecture pieces. Tomorrow we're going to do some work with this drugs in the nervous system piece. But as far as this, I'm going to stop.